Let's look at some examples with multiplying some rational expressions. If I had radicals, if I had square root of 25 times square root of 4. Now, let's show where this is headed. Square root of 25 is 5. Square root of 4 is 2. 5 times 2 is 10. But what I want to show is, when we multiply radicals, multiply your two radicands and notice 25 times 4 is square root of 100 is 10. Now, when the numbers end up being these perfect squares, obviously that would be the shortest, but what we're trying to show here is that we do have what's called the product rule. What I'm allowed to do is if I have square root of a times square root of b, I'm allowed to take the product square root of ab. I'm allowed to multiply. If I'm multiplying two radicals, I can multiply the two radicands. When we see this is square root of 2 times square root of 7. If those are the same index, what I'm allowed to do is multiply this as 14. If I were to even see it as polynomials, square root of x plus 3 times square root of x minus 3, you can put those in parentheses. Remember that if I were to take a product of x plus 3 times x minus 3, well, we may remember, and we could go through and FOIL this whole thing. X squared, I get a negative 3x, I get a positive 3x, which are going to cancel, and I get a negative 9. My simplified answer, square root of x squared minus 9. I'm allowed to multiply my two radicands. This even works even if my index is not a 2. If I have cubed root of 6 times cubed root of 7, what is critical is they end up being the same index. As long as they have the same index, I keep the index, and I can just multiply the two radicands. For whatever that index is, as long as it's the same between the two radicals, keep it, and I can multiply the two radicands. I can use this to multiply and combine, but most importantly, let's show when we use it to split up two radicals.